Today, I'll be giving a brief presentation on the layer-wise decomposition of ResNets for distributed training. This is a joint work between Chin Dun and Cameron Wolfe, PhD students in the Department of Computer Science in Rice University, who are advised by Dr. Tassos Krilitis, who is also a member of the Computer Science Department at Rice. The motivation for this work comes from three different areas. First, the area of distributed training for machine learning. Second, the area of stochastic depth residual networks. And third, the area of independent subnet training, or IST for short. So we know that training deep learning models is expensive, but we can use distributed training to make it faster. The canonical approach is to use some kind of synchronous distributed method, but this can introduce very large communication bottlenecks. Previously, it's been shown that residual networks are robust to the removal of entire layers, and furthermore, we can view them as a Euler discretization, where dropping layers from the ResNet just yields a coarser approximation to the same continuous transformation. If we view these ideas in the lens of independent subnet training, which shows that we can independently train subnetworks to form a high-performing global model, we can create a methodology for layer-wise decomposition of ResNets for independent training so that we can train ResNets synchronously with less communication. Our methodology is as follows. First, we randomly initialize a global residual network. In our case, we use the pre-activation ResNet 101, which can be seen in the upper right-hand corner. We decompose this ResNet in a layer-wise manner, distributing its layers to n different subnetworks evenly. We distribute each subnetwork to a separate machine, which allows us to only communicate the parameters partitioned to a particular subnetwork. We train the subnetworks independently and then aggregate their updates into the global ResNet. Then we repeat these steps until the convergence of the global model. The process of partitioning layers to different subnetworks can be seen at the bottom figure. We test this distributed training methodology across a variety of image perception datasets and find that even partitioning into 8 subnetworks leads to minimal loss in accuracy while yielding very large speedups in training. This speedup comes from the combination of independent distributed training of subnetworks, the fact that the subnetworks are shallower than the global networks, and the fact that we can communicate fewer of the total parameters. We find that being more particular about the layers that we partition to subnetworks can lead to improvements, as well as by overlapping some layers between different subnetworks. In future work, we want to explore different smart methods of partitioning the ResNet, as well as adding stochasticity into the partitioning process.